Today, Caryanne Willson will be giving a lecture over the physics of neutrons as they relate to radiation detection. Caryanne has a bachelor's in science from Georgia Tech in nuclear engineering, and her current specialization is in neutron detection for safeguard applications. For general housekeeping, please just use the Q&A function throughout the lecture, and we'll answer these questions at the very end.
Hi everybody, my name is Caryanne. So I'm gonna go ahead and share my screen and get started with the lecture. All right, so welcome to the lecture on neutron physics and detection. So I'm gonna start very basic. What is a neutron? It's a neutral subatomic particle, and it has a rest mass close to 1 atomic mass unit, or 939 MeV per c squared, if you prefer that unit. And so for the sake of this lecture and how we detect neutrons, we're gonna group them into kind of two energy groups. But there's obviously a huge range of neutron energies that you can get more and more specific with the classification. So when we talk about slow neutrons, we're talking about less than 0.5 electron volts. And then a lot of times we'll also talk about thermal neutrons. And so that is about 0.025 electron volts. This is kind of like room temperature, or when the neutron is in thermal equilibrium with the room. When we talk about fast neutrons, we're talking about neutrons greater than 0.5 electron volts. And this division is called the cadmium cutoff. So on the right side of the screen, you will see the cross sections for cadmium. That's the one in red. And so you see right around 0.5, it really drops off. But below that, it's pretty high. So the interaction probabilities vary strongly with neutron energy. And so capture reactions will dominate at lower energies, and you see less capture at higher energies. All neutrons are born fast. The average fission neutron for uranium-235 is born at approximately 2 MeV. And then the neutrons will be moderated in the environment. The average number of scatters on a specific element to thermalize a 2 MeV neutron is shown here. So if the nucleus the neutron scatters off of has a lower atomic weight, the neutron can deposit more energy onto that nucleus, so it takes less collisions to thermalize. A really good way to think about that is like if you're playing pool and you have pool balls, if you have a neutron and a hydrogen atom, which is the same size, so that's two pool balls, they scatter off of each other, and if you like throw it at it, it'll cause the other pool ball to move. But like let's say you have a pool ball and a bowling ball, which could be something like uranium, then the pool ball will be more likely to bounce off of this very heavy bowling ball. So that's kind of a way that makes it easy to think about. And so yesterday, Sander talked to you guys about gamma rays and gamma decay. And so a lot of sources, when they're excited, emit gamma rays. But on the right side of the screen, you can see the average binding energy per nucleon. And so it's pretty high, the scale of MeVs. And so a neutron would require the nuclei to be extremely, extremely excited to emit a neutron to de-excite. And so we don't see pretty much any neutron sources from the de-excitation of an excited nuclei. So now I'm going to take a second to go over some of the different types of neutron sources, so that way we can inform maybe the best way to detect these kinds of neutron sources. So the first thing we're going to talk about is spontaneous fission. So this is things like Californium-252 or plutonium-240, that the isotope will spontaneously fission and then emit some amount of neutrons. This is 3.67 or 2.21 average neutrons. It doesn't always emit exactly that many. Obviously, you can't emit fractions of a neutron, but generally between 2 and 3 neutrons per fission, and those can be detected. The energy of those neutrons follows the Watts fission spectrum. So the average energy of that being 2, the most probable energy being 1. And there's usually a very small percent chance that these isotopes undergo spontaneous fission. The rest of the time, they're typically alpha decaying. So for Californium, this is a 3% chance. So then from this chance and from this neutron number of neutrons per fission, you can get the average neutron rate per gram. And that's kind of the same with the plutonium-240 as well. So there are other neutron sources called alpha N sources. So what happens with these types of sources is that you will have usually an actinide. So when you think of these, you think of plutonium or americium, that will alpha decay. And then something else in the source will capture the alpha, and that will transmutate and emit 1 neutron during that. So for what we call a PUBI source, this is plutonium and beryllium. The plutonium alpha decays into a uranium isotope and an alpha particle. And then that alpha will interact with the beryllium in the source, leading to carbon-12 and a neutron. These have different energies and typically a spectrum. So PUBI and AMBI have 4.5 MeV because this is due to the binding energy of the alpha and the beryllium. So that's how you determine the average neutron energy, versus AMLI is a lot lower just because like these are different isotopes. And then as you can see, the spectrum for an alpha N source tends to look a lot different than this very like clean Watts fission spectrum that I showed in the previous slide. And then going over one more potential neutron source. So you can get quasi-monoenergetic neutrons emitted by accelerated charged particle fusion. And so these are either deuterium-deuterium or deuterium-tritium reactions, where a deuteron will be accelerated towards a target. That target is deuterium for the DD reaction, and it's a tritiated target for the DT reaction, and that will emit high-energy neutrons. And then you can see these reactions down here. So when we talk about gamma rays, those are ionizing radiations. So they have coulombic interactions in detectors. Alpha and betas are charged particles. So those also have coulombic interactions in the detectors. But the neutron has to interact with the detector material in a way that will eventually emit an additional particle or create some kind of additional particle that will then cause ionization. So slow neutron detection is typically absorption reactions, where the neutron will be absorbed and a nuclear reaction occurs, transmuting the target nucleus into a product nucleus in a proton alpha or gamma ray. And then we can do a couple things to detect fast neutrons. So we can moderate the neutron down to a thermal energy and then use one of these methods. Or a neutron can scatter off of a nucleus, and that recoil nucleus can then ionize in the detector and deposit the energy. A high energy neutron can also cause a reaction that produces a proton or an alpha. But these reactions are endothermic, so they're usually threshold reactions, and the neutron needs sufficient kinetic energy to make this happen. So we're going to go through all of these different types of interactions, and then detection techniques based off of this specific type of interaction. Before we do that, I want to take a second to talk about why we really want to be able to detect neutrons. So thermal neutron detectors can be used to monitor the flux of a nuclear reactor. And this parameter is used to assess power density, and just make sure that everything in the reactor is running as expected. Neutrons are also a very unique signature of nuclear material. We're talking about uranium and plutonium here. So we can use neutron detectors to ensure that fissile material is accounted for. We're thinking about all different parts of the fuel cycle, enrichment plants, spent fuel, any time or place where it may be easy to divert material for non-peaceful purposes. And then these same principles can also be applied to Homeland Security. And so oftentimes the Department of Homeland Security will set up portal monitors containing either scintillators or helium-3 to detect neutrons at ports and borders. And this can help prevent smuggling of sources in and out of the area. And it can also be used at in lab spaces to monitor for contamination. So here are the interactions that we'll be talking about. So for scattering, elastic and inelastic ones. And then for absorption, we'll talk about radiative capture, capture transmutation, and induced fission. And so there's a likelihood of all of these reactions happening. This is called the microscopic cross-section. And each type of interaction has its own specific microscopic cross-section. It's usually given in the units of barns. This unit actually came about in the Manhattan Project when the scientists were fissioning uranium, and the thermal neutron cross-section for that is as big as a barn. So it was really easy to hit, and that's where that unit came about. So you can get the total interaction probability by summing up the probability of all of these, all of the cross sections, and then we can look at the probability of a specific interaction as the microscopic cross section of that reaction over the microscopic cross section of all reactions. So I just defined microscopic cross section, but that's a quantity. And then the macroscopic cross section is the quantity that discards the likelihood of the interaction for a given volume. So to do that, to get that value, you'll just multiply the microscopic cross section by the number density. And the macroscopic cross section is usually in units of per centimeter. And then one more thing I want to talk about with cross sections is neutron attenuation. So if you know the initial intensity of your neutron source, it's an exponential of the negative macroscopic cross section and the thickness of that material, and then you can determine the intensity of the neutrons on the other side of that material. So let's say you had the sheet of polyethylene or something, and you knew the neutron rate into the polyethylene, you could figure it out on the other side. Okay, so jumping into these reactions, first we're going to talk about the radiative capture reaction. This is the most probable interaction in most materials that causes attenuation or shielding, where the material captures a neutron, and then the nuclei that captures the neutron is in an excited state, and it de-excites by emitting a gamma ray. These are typically used in indirect detection techniques such as activation foils. So activation foils are usually metals that do not fission. So this is actually talking about some work that I've done in the past year, but the copper 63 N2N reaction is a pretty standard reaction used for fast neutron activation analysis. And so as the copper foil or copper sample is radiated it'll undergo this end-to-end reaction and the amount of copper-62 in the material will build up. And then once you stop irradiating it, it will decay away, and you can use the time that you can use an external detector and put your copper foil in front of that. So that could just be any like sodium iodide or high purity germanium detector. And it will measure a 511 keV peak. And you can use the integral of that peak to be able to determine the neutron output. So this is one of the spectrums that I measured from some copper activations at various neutron outputs. And you see this really prominent 511 keV peak that is from the beta plus decay of the copper-62. So those will emit 511 keV gamma rays when the positron annihilates. So some pretty big advantages and why you would want to use this is they're really sensitive, and gamma ray interactions won't affect your signature if you're irradiating it with gamma ray. But you need you need to make sure you're matching the right foil to the right neutron source, and looking at those threshold and reaction probabilities. And then you also just need to, like, for the most part, like pretty well characterize your environment. So for the next type of reaction, we're talking about capture transmutation reactions. So this is what a lot of capture-based detectors are based off of, where a isotope will capture a neutron and then transmutate into another isotope and a charged particle. So for helium-3, when that captures a neutron, it becomes a triton and a proton. And then lithium-6 is another common one, where it becomes a triton and an alpha particle. So these are used to indirectly detect neutrons because they have a higher Q value. And the cross sections are higher for thermal neutrons. So this kind of detector has better efficiency than scatter reactions. So this does make the momentum and energy balance important in the detector design. And you can actually calculate how much energy is given to each of these particles based off of the Q value of the reaction. So here are some of the most common capture-based detectors. So BF3 proportional tubes, boron-line proportional counters, and helium-3 proportional counters. Helium-3 is often considered the gold standard due to its high neutron detection efficiency. It also has good gamma ray discrimination, and the gas is non-toxic, versus BF3 is a hazardous gas. Cross sections are shown to the right. For thermal neutrons, we're in the 10 to the 3, 10 to the 4 Barnes range. So we're going to go ahead and talk about some of these in more depth. So this is the BF3 tube. A boron-10 isotope will absorb a neutron and produce either one of these reactions. So lithium-7 in the ground state and an alpha particle, or lithium-7 in the excited state and an alpha particle. When the boron undergoes these reactions, since the reaction products will be emitted in equal and opposite directions. In a really large tube, the interaction is more likely to happen towards the center, so both products deposit their full energy. But in smaller tubes, one particle may escape the detector before it deposits all of these energies, which will cause this wall effect you see here. So this would be like in an ideal case where there's no wall effect. You can see each of the individual reactions here. This bigger peak for the excited state and this smaller peak for the non-excited state. But then when you have a smaller detector, you see this wall effect where the alpha will deposit up to its full energy, and then you get up to the full energy of the, well, you get the full energy of the lithium and some of the, and then you see the full energy deposition peaks there. This is caused by interactions close to the wall. And then also you kind of see this low amplitude events. This is from gamma rays when they scatter off electrons. But in gas, electrons usually have a very large range, so they can be easily discriminated. So this is a tube that has the same reaction as the BF3 proportional tube, but the boron layer is kind of aligning on the outside of the detector instead of just the gas throughout the detector. So as you increase the thickness of the boron layer, the neutron will be more likely to interact. However, the reaction product will lose some of its energy as it moves towards the detector. So basically, if the lithium is deposited, if the lithium is emitted in the direction of the detector, it will deposit up to 0.84 MeV. And if the alpha is emitted in the direction of the detector, it will deposit up to 1.47 MeV. So this detector kind of has the disadvantage that it's not gamma blind because you would see some energy depositions in this lower energy region too. And you can't just cut that off or set a threshold. And then I believe that this is the last capture reaction that we're going to talk about, but this is induced fission. So this is more probable at lower incident neutron energies, thermal neutron energies for uranium-233, 235, and plutonium-239. And then for uranium fission, I believe about 200 MeV is emitted. And so the number of neutrons and identity of the fission fragments differ from reaction to reaction because obviously this fissions, it'll emit some amount of neutrons like we talked about earlier, and then have some fission fragments. These are the distributions of the fission fragments right there. And each fissionable isotope has a unique distribution for these fission fragments. So we can take advantage of this in a detector such as a fission chamber. So this is really similar to the boron line tubes, but it's lined with a layer of highly enriched uranium so that it's extremely sensitive to thermal neutrons. So the thermal neutron will induce fission and a large amount of energy will be deposited into the fill gas. It makes it super easy to discriminate neutrons from gamma rays, especially if you think of high flux environments such as like bent fuel or things like that. But these are operated in current mode in these high flux environments. So we don't usually see individual pulses. We see the average current over a certain time period. So that was a pretty good overview on how to detect fast or how to detect thermal neutrons. But now let's take a second and talk about like why we would want to detect fast neutrons. As we talked about earlier, all neutrons are born fast. When we moderate them to detect them, we're losing energy about the information and the timing. If we know information about the energy, we can understand more information about the source. So if you look at this image at the top right side of your screen, this compares a Watt fission spectrum from a californium-252 source to an alpha N energy spectrum from a Kubi source. These two have extremely different spectra. And by looking at those spectra, you can, it's really indicates what type of source it is, which is important for many applications. The main one that I work on being safeguards applications. So cross sections vary highly with energy. So we just talked about thermalizing neutrons. Well, I guess we talked about thermal neutron detection, but we can also thermalize fast neutrons using moderation and then detect those thermal neutrons. Or we can also talk about some scatter-based detectors. When we decide to moderate neutrons, eventually, if you get a thick enough moderator, it will reduce the detector efficiency. So the typical moderator we use is between a couple and tens of centimeters. Um, so first of all, for a moderating material, you're going to want to use something that a neutron can deposit a lot of energy onto, such as hydrogen. So a lot of the examples that we'll be talking about, or applications you see are polyethylene or water. But here's an example of fast neutron detection through moderation. These are Bonner spheres. So a lithium iodide scintillator is placed in the center of a polyethylene sphere. And then based off of the moderator thickness and the neutron energy, the count rate will change. And you can apply unfolding to get some more information about the spectrum. So this plot shows the relative response per neutron depending on the moderator thickness. So obviously when there's no moderator, the lithium iodide scintillator, which is based off of these lithium reactions, has the highest relative response to thermal neutrons. But when you add like 8, 10, 12 inches, you can see it kind of peak between 1 and 10 MeV, and it'll make it much more efficient with fast neutrons. And a lot of times this is used in dosimetry. Just want to mention that. So there are also helium-3 detectors that are embedded in a block of high-density polyethylene, and the neutron will scatter to thermal energy and then diffuse into the detector. This process takes time. So the neutrons will thermalize really quickly, but it takes a while for them to diffuse into the detector. This increases the time scale of detection. This increases the time scale of detection to the order of microseconds. And sometimes timing information is important, and you want to know that specifically with neutrons. All right, so now we'll be going over some of the scattering interactions and how we detect with that. So neutron elastic scattering conserves energy and momentum. So incident neutron will interact with a nucleus, and the scattered neutron will go one way, and the scattered nucleus will go another way. And you can solve for the recoil energy of the nucleus using the equation on the bottom of the screen. And you can, of course, derive this if you want to derive this using these two equations, conservation of energy and conservation of momentum, and get this equation. But for the sake of time, we're not going to be doing that. So here's just kind of an example question to get the point, but it's what is the maximum and minimum recoil energies if the incident neutron has an off of hydrogen, if the incident neutron has an energy of 2.45 MeV. So in this scenario, A, which is the ratio of the neutron mass, or the ratio of the nucleus to the neutron mass is 1 because it's a hydrogen nucleus and a neutron interacting with it. So it will have the maximum recoil energy at 0 degrees. In this case, the neutron would transfer all of its energy to the hydrogen nucleus, and then that would be 2.45 MeV. Then you could probably guess that the minimum recoil energy of the hydrogen nucleus would be at 90 degrees if the neutron just completely like bounces off of that hydrogen nucleus and backscatters. And so that would be 0 MeV and 2.45 MeV would go to the neutron. And then there's also inelastic scattering. So the neutron is absorbed and re-emitted and forms compound nucleus. And some of the energy will be absorbed in the recoil nucleus, and the nucleus will de-excite by emitting gamma rays. This is a threshold reaction where epsilon 1 is the first excited state. This has a very low cross section for small nuclei, and it doesn't occur for hydrogen, which is a lot of how these scatter detectors work, but it is important for uranium. So when we are detecting neutrons through scattering, a lot of times we are using scintillators, particularly organic scintillators. So organic scintillators are made up of hydrogen and carbon, and the neutron will elastically scatter off of the hydrogen, causing a proton recoil. And this is what causes the scintillation. The neutrons will also interact with the carbon and scatter off of that, but because this carbon is much heavier, the light output from the recoiling carbon nucleus is extremely quenched. And then gamma rays also interact with this detector by Compton scattering off of electrons, which can also induce scintillation. So these cubes usually have a pretty low density around the wall. Because of this low density, though, most of the gamma ray interactions will be Compton scatter. There won't be any photoelectric absorption, and so you won't see a full energy gamma peak from gamma deposit, gamma interactions. So in scintillators, you have prompt and delayed fluorescence. The portion which affects the tail of your pulse that you observe from the scintillator, the portion of light output in the delayed component depends on the type of interacting particle. And so because of this, you can differentiate the pulse shape from the neutron and the gamma and tell what kind of interaction is from which particle. And so this is just an example of how those pulses look different. So as you can see, the neutron has more light output in the tail than the gamma ray does. So we can do this technique called pulse shape discrimination, where you take the ratio of the tail integral of the pulse to the total integral to determine what kind of particle is a neutron and what is gamma ray. And because neutrons have more delayed fluorescence light output, they have a higher tail to total ratio. So you plot this integral, and then you can plot light output in KeV. And the top is the neutron band, and the bottom is the gamma ray band. Discrimination also depends on the amount of energy deposited. So at higher light outputs, it's more prominent. And then actually, I just want to make a point about light output. So obviously the gamma rays interact with the electrons, which have a linear light output, but protons are a little bit heavier, and so they're going to be a little bit more quenched. And so that light output is not directly linear with energy deposited. And I'll talk about this a little bit more when I talk about time of flight, but KeV EE is kilo electron volts electron equivalent. And so that's what we refer to in light output because this isn't a direct measure of the neutron energy being deposited in the scintillator. So in organic scintillators, you can detect fast neutrons directly, and the scintillation process occurs very quickly. So you know exactly when this neutron is detected. For the trans-still beam detector, when we talk about timing resolution, we're usually talking about timing resolution of a system. But if you put a sodium-22 source between them, you can detect one 511 keV photon in this one and one 511 keV photon in this detector. And those are emitted simultaneously from the positron annihilation. And then you can apply a Gaussian fit to understand the timing resolution. And you can just get a very good idea of like when this event actually occurred. So, as I mentioned on a previous slide, organic scintillators are difficult to characterize because energy and light output are not linear. So what we can do to kind of like characterize the light output from neutron interaction is what we call time of flight measurements. So a spontaneous fission source will emit multiple neutrons and gamma rays, and you have two detectors. So you can see a trigger detector next to the spontaneous fission source, and then another detector that's put at a further distance away from it. So the trigger detector will trigger when the first particle interacts, and then the second will trigger when the second particle interacts. And you should get a good amount of these interactions because, like I said, spontaneous fission source emits multiple neutrons and gamma rays, and these organic scintillators detect both. And so if you know the distance between your trigger detector and this detector that you're trying to characterize, you can determine the neutron energy. So in the top right-hand corner of the screen, you see this TF, which is like the time between the trigger and the neutron detector. And then it's a function of distance and energy. So you can solve this for energy, but this equation is derived from the kinetic energy equation, or 1/2 mv squared with the mass of the neutron. So if you plot count rate as a function of time difference between like these two pulses, you get a plot that looks a lot like this. So gamma rays travel at the speed of light. So if you get a gamma ray trigger and then you detect a photon in the detector you're trying to characterize, you get a really short time difference versus neutrons, you get a much bigger time difference because they do have mass and don't travel at the speed of light. So the peak occurs at the most probable neutron energy, which is about 1 MeV for a Californium-252 measurement. So the longer it takes a neutron to travel, the lower its energy is. So if we take this plot and convert it to a light output spectrum, we get this. And as you can see, light output isn't linear with energy, so we need some other function to convert this light output to an energy. And that is done. This photo shows calculation of like Burke's parameters, but you basically just like develop or like use a function developed in literature to be able to convert between light output and energy of a neutron. And then high energy neutrons will have less quenching, so you get more light output per MeV deposited. So that's what defines the shape of this. And then I want to talk about one more type of scintillator, just because this is something that I've been working with for the past year. And I think it is a really interesting detector and it's pretty fun. Helium-4 scintillators. We talked about helium-3 earlier. This is a little bit different. Helium-4 is just like, I guess, plain old helium, or like party city helium, which you go and get like balloons filled up with. And because this is a gaseous scintillator, it is gamma ray insensitive. So the neutrons will still interact with the helium-4 gas, and the helium-4 is light enough that the neutron can cause that nuclei to recoil. But because it is a gas, when the gamma rays Compton scatter off the electrons, the range of the electron is typically much larger than the size of the detector. And so it usually won't deposit all of its energy. Because it's a noble gas, there's no quenching. And so it has an extremely linear light output for neutron detectors. So you can kind of see this quenching down here. And then this is a table just like summarizing the range of an electron in this gas. So when we work with this detector, we can usually just like set a threshold around 300 keV. And when we set that threshold, we eliminate almost all of the gamma ray counts because this range is so large. It'll deposit way less than 1 MeV. And then this shows the spectrum of a cesium-137 source. So you can see here that there's like very clearly very little energy deposition, and by applying a threshold, we can basically eliminate gamma ray counts. And then we have some different measured spectrum here. And just because of the mass of the helium nucleus, a neutron can deposit up to 64% of its energy on it. We work with the Arctis helium-4 detector. So what I will say is the disadvantage of this is that the pressure of this is 198 atmospheres. So kind of just a summary of these capture and scatter detectors. Helium-3 is the conventional neutron detector for neutron timing measurements. Because it does have a very high thermal neutron capture cross-section for these moderated neutrons. But because you're adding moderator around the actual detector, it will expand the scale of these interactions to microseconds. And then helium-3 is also pretty expensive to produce. Helium-3 is produced from tritium, and so that's like from the weapons program. Versus organic scintillators have a much lower detection efficiency when compared to helium-3. But because it's a scatter-based detector instead of a capture-based detector, it allows nanosecond precision of correlated events. And this can be really good in some cases, such as multiplicity counting, and then you can also like measure more particles because the pulse coming out of this is much faster. It's also less expensive compared to helium-3. So in summary, I talked about some of these capture-based detectors that are really great for detecting thermal neutrons. And in a lot of them, you can discriminate photons based on energy. And then scatter-based detection, which is done in organic scintillators, or as I mentioned, helium-4, and they're very sensitive to fast neutron sensitivity. And in these organic scintillators, you can discriminate between photons and neutrons based on the shape of the actual pulse. And both of these types of detectors have their advantages and disadvantages. So it's important to think about all the parameters of what you're trying to detect and what the most important information is to you when you're selecting these detectors to do your own experiments. So with that being said, I am more than happy to take any questions.
All right, thank you, Caryanne, for that presentation. There are a few questions in the Q&A section, and I'll start reading through them. Here's one. Thank you, Dr. Caryanne Willson, for your insightful lecture on the neutron physics and detectors today. The question was, considering neutron detection in mixed radiation fields, how can one effectively discriminate between fast neutrons and high energy gamma rays when using organic scintillator detectors such as EJ301, especially under high count rate conditions?
So it does get a little bit more difficult under high count rate conditions. because what you will start to see is pulse pileup. And so you look at this picture of this pulse, but when you're in a really high count rate condition, you may have another pulse like right here. Um, and so that will obviously like alter the shape of your tail to total ratio. So I guess there are like two different ways you can do this. The first is you can implement some type of like pulse cleaning, where you can in your data analysis scripts implement parameters to determine if you have two pulses there, and then you can throw out that data. Um, there's also been a lot of work done to do to develop like pulse recovery algorithms so that you are not throwing away all of that data, and you could potentially look into that and implementing some of those scripts in your algorithms. And then also, um, there are definitely like things you can do in your experiment that will probably be less effective. But if you like add gamma ray shielding in front of your detectors, that like could potentially help. But I think that the way that you handle your data in post-processing will be much more effective.
Right, thank you. There's another question on helium-4. Considering that helium-4 scintillators are gamma insensitive and deposit a significant fraction of neutron energy, how might we further optimize their geometry or pressure conditions to enhance discrimination between neutron energy spectra, particularly for applications in high background environments like nuclear safeguards?
Um, how the question is, how do we optimize the geometry and the ability to discriminate between neutrons and gammas in safeguards. And so actually Oscar Surface, who did a lot of work on this, has a really interesting paper where he talks about using the helium-4 detector for a photon active interrogation setting, which obviously has a very large photon background. And he talks about setting the threshold of the actual detector and like a technique to basically like more specifically set the threshold of the detector to be able to eliminate gamma rays from this detector. When you're talking about neutron detectors, this is usually called like the parameter is called like Caryanne or something, like when you're just like looking at neutron counters. But also in this paper, he details how he described it to this. And so it's already like been well proven that this detector is really good at doing neutron spectroscopy in high count rate environments. Um, and so I guess like the next thing would be like finding other applications to apply it to.
There is a question on in which branches or industries is neutron activation analysis used?
Um, so neutron activation analysis is used for reactor diagnostics. You can also use it, trying to find the slide. Oh boy. Um, so it is used for reactor diagnostics and measuring the flux in neutron reactors with thermal reactions. It's also used for fusion experiments, and you can use a broad variety of activation foils for that. You can use it in borehole logging to monitor the output of the neutron generator. that is used for those applications to make sure that you have the most accurate calculations possible. And you can also use it just for like generator calibration for active interrogation. A lot of times when you are using these accelerator-based fusion sources, it is pretty important to know the output of those generators so that you can basically like take the minimum amount of time for active interrogation and still have like the maximum or I guess the minimum rate of like false negatives. So it's pretty like broadly applicable, especially because it's immune to pulse pileup because it's an integrating detector.
There's another question about applications. How are neutron detectors able to operate inside nuclear reactors, considering the extreme conditions such as pressure and radiation damage?
Mhm. Um, so like I said, a lot of times you can use neutron activation foils because those are kind of like immune to that. And then you have like a rabbit system to move the activation foil to a detector, basically count it with a detector that's in a remote location. Or you can use these fission chambers that relies on the thermal fission of uranium-235. And so with the fission chamber, the fission products are really high energy, and those are deposited in the detector instead of like gamma rays in this gas. So as we talked about, gamma rays won't deposit as much energy in gas, and then you have these like pretty heavy. I mean, like you're looking at mass numbers between 70 and 160 fission products that are depositing much more energy into the fission chamber. And then you're also operating this in current mode rather than in pulse mode. And so that also helps with the high count rates.
For fast neutron detection, there's a lot of talk in this presentation about moderating our neutrons. And their question was, if you're moderating neutrons, how do you go about measuring initial energy? And how do you predict how much moderation is going to be applied to moderate your neutrons in applications?
So when we're moderating neutrons, we can do something like this where we can kind of approximate the initial energy based off of the thickness of the polyethylene. But I think that this is one of the really big advantages of organic scintillators as opposed to moderated capture-based detectors is organic scintillators will give you initial neutron energy. So if that's a parameter that you're really interested in, then it would probably be better to use an organic scintillator. But you can optimize the amount of moderator by doing this basic attenuation calculation that I showed at the beginning, or by using simulation to do that.
There was one that was related to neutron capture therapy, and the question was, how can we indirectly detect and quantify neutrons for boron neutron capture therapy?
Um, I'm actually not super familiar with boron neutron capture therapy. My background is mostly nuclear engineering and not medical physics. And so would it be okay if we went ahead and moved on to the next question?
For sure. There was one, when doing field work, what's the ideal neutron detector?
Um, I don't think you can say that there's like an ideal neutron detector for any one application. It really like depends on what you're interested in. So if you want like high efficiency for thermal neutrons, then maybe use a capture-based detector. If you just want to count fast neutrons, maybe you can use a moderated capture-based detector. If you want really precise energy and timing information, then it might be best to look towards organic scintillators. Or if you're detecting fast neutrons and you want them to be, and you're detecting fast neutrons in an environment with really a high gamma ray background, then maybe it would be best to look into using a helium-4 detector for this application. Um, Field applications is really broad, and you can do neutron detection for many different things. And so you have to look at what is the most important parameter that you want to optimize for, and then look at the characteristics of each detector and make that determination.
There was one question asking for clarification on discrimination between neutrons and gammas within a scintillator, organic scintillators.
Um, so basically, the way that the neutrons and gamma rays interact with the detector, the gamma rays will interact with electrons versus the neutrons will interact with protons. And so the proton interaction will emit more light through a process called delayed fluorescence versus than the electron interactions. And this is obvious when you look at the shape of the pulses from this detector. And so you can see in blue here, this is a neutron pulse. And you can look kind of like after 400 seconds, the neutron pulse has much more energy than the gamma ray pulse. Um, so you can take the ratio of this tail integral of the pulse to the ratio of the, or take the ratio of the tail integral of the pulse to the total integral of the pulse. So like let's say from like 200 to like 1,000 nanoseconds. And we call this the tail to total ratio. And we can plot a 2D histogram of that versus light output. And you'll see this triangle or this band of pulses that has a higher tail to total ratio. And that is the neutron pulses. And then the band of counts that has the lower tail to total ratio is the gamma counts.
All right. There was another question asking for like specific additional reading that you would suggest for neutron activation, like what has helped you personally.
Um, for neutron activation analysis, um, I would specifically go into Glenn Knoll's textbook. In chapter 19, they have a like very good description of this process and how this process is used. Um, and then you can kind of like dive more into the literature from there. But I think that that is a really great starting point.
Right. I think that's about it for today. We have hit 2 o'clock. Thank you everyone for all those questions, and we'll see you tomorrow for David's talk on gamma detection and far field search.